This is a video to support Lecture 2 of the robotics course and also complement the beginner tutorials for ROS, establish a connection between workshops, lectures, and labs. In robotics, there's a need to build several responsibilities and distribute them in independent modular components, or in the terminology of ROS, nodes. A common software architecture for this is a Blackboard architecture, so that there is a common API for every sender and every consumer of information. They just need to know that API to the middleware. In ROS, the middleware is played by a particular piece of code that when it runs is called ROS core and registers which nodes are publishers, which ones are subscribers, which are servers, and so on. The first type of software pattern that ROS enables is the publisher subscriber. This is for an information producer to forward information to a consumer. In ROS, it's very common that sensors produce information, and so they become publishers. Therefore, in ROS, publishers are senders when we think of the Blackboard architecture. The C++ code of a publisher needs to include the ros.h file for linking statically against the ROS infrastructure. It also needs a dynamic constructor handle to connect with the ROS core middleware. And also it needs to have an object to the class publisher which advertises that in this node we host a publisher. The information that flows across nodes is messages, and they are posted on topics. Therefore, topics are named channels that also indicate the data type of the message. Messages are data, and therefore they have a certain type. ROS has predefined types. To the finite compile time those types, their corresponding .h file must be included, and that type is used in the constructor of the object publisher. You can publish the same type, in this example strings, into channels, so channels must be also named. In ROS, the model of communication for the receiver is a subscriber. Therefore, the very first step of this software architecture is to register the function that is going to act as a callback. So the receiver must indicate to the middleware where does it want to be invoked when messages are received. This follows the principle of software engineering. Don't call us, we call you. So ROS core enacts an observer pattern and is an example of inversion control. Any node must have links to the middleware. So a node hosting a subscriber needs, like for the case of the publisher, some common element. It needs the include file for the ROS infrastructure. It needs to construct dynamically a node handle, and it needs to create an object of the class subscriber. Subscribers subscribe to topics, and as we mentioned, these are named channels which offer data in messages of a certain type. We subscribe in order to obtain the data of the message, so we need to include the definition of that data. That data type is used as the argument of our callback for defining the type of the message, and constructing a subscriber needs to identify the name of the channel and also which is the callback to enact when messages are received in that channel. ROS is a particular example of push technology, and in the lecture we contrasted that technology with other alternatives. ROS also offers another mechanism of interaction, which is another pattern called client-server. In this case, there are 4 steps. First, the client issues a request. The request goes through the middleware and is forwarded to the server. The server runs some function and produces a response. That response is returned to the middleware, and the middleware forwards the response to the original requester. In the case of ROS, the servers are called services. Before interactions between a client and a service happen, some amount of setup has to be produced. That setup is first on the server. The server must have a function that implements the transformation of the values or parameters received in the request and run some software in order to produce the response. The service could be something very simple, as in the ROS beginners tutorials where we add 2 integers, or it could be a complicated service where a full stream of video is processed to identify an object. If a node hosts a service, we're going to also have to include and program the common elements of the ROS middleware. But for the request and the response, we're going to have to define the data type of the service. And in ROS, both the data type of the request and the response are defined in the same file. Like any ROS node, we're going to have to include the ros.h file for the ROS infrastructure. We're going to have to invoke a constructor to hit a ROS handle. But here, when we create an object of the class service server, we are also advertising that this node hosts a server. The parameters of the function that implement the service must use the data type defined for the request and the response. And when we advertise the service, we indicate its name and also what is the function that implements the service. Now you see the advantage of this decoupling. There could be many clients for the same service. What is the structure of a ROS node that acts as a client? Well, it has basically the same things. It has to include the ros.h file for the ROS infrastructure. It has to construct a node handler in order to connect to the middleware, and it has to indicate that it is a client. Compilation needs to know the data types of the request and the response, therefore of the service. Services are named, so we need to give the name of the service we want to connect. And within the service, what type of service, what function do we want? Actually, the same service could provide several functions that implement computations. Okay, that covers the setup. Now let's look at the action. How does a client invoke a service? Well, it has to build the request. It has to invoke, basically call that remote function. It has to wait for that function to return, and it has to check if the call was successful, because maybe we could not reach the service. If the call was successful, we can extract the response. ROS today is the most widely used middleware for programming robotics and in some cases embedded systems. It has several advantages. API to the middleware has been standardized, but you can extend the topics or the services. The components of a robotic system are several threads running as nodes in the ROS system, and a node can play many roles. So a node can be a publisher and a subscriber at the same time, or it could be a filter. And so it's a very versatile way of constructing sophisticated architectures. Moreover, ROS has a series of tools to support the development and the understanding of what's going on. 2 of these tools are very important. One of them is ROS Topics, which allows you to check what is being published in the system, or actually impersonate a publish and deposit some message in the middleware. And the other one is ROS Services, which similarly allows you to inspect what services are there, what are the parameters that they need, who is running them, and more importantly, you can also test them by invoking a service. Whether you completed the beginner's tutorials of ROS or not, I hope this video gives you some context of what is the software architecture supported by ROS.